Good morning, everyone. Welcome to today's webinar on Forensic Geotechnics concepts and case studies. I'm Pooja Dobhal, Marketing Coordinator at Sengers, and your moderator for today's session. Geotechnical failures can have significant consequences, making forensic geotechnics a crucial discipline in understanding, analyzing, and preventing such failures through real world case studies. Today's session will provide valuable insights into how forensic geotechnical investigations help identify the root causes of failures and improve future engineering practices. It's an honor to introduce It's an honor to introduce our esteemed speaker, Mr. Ravi Sundaram, Director of Senjus Geotechnica Private Limited. With over 44 years of experience, Mr. Sundaram has made remarkable contribution to geotechnical engineering, particularly in geotechnical contribution to geotechnical investigation, forensic geotechniques, and foundation engineering. A recipient of multiple prestigious awards, including the IGS Professor Dinesh Mohan Memorial Award. He has published over 70 technical papers and active contribution to standards and guidelines as a part of BIS and IRC committees. We are privileged to have him with us today to share his expertise in forensic geotechnics throughout insightful case studies. Before we begin, I encourage everyone to participate actively. Please drop your questions in the chat box and we will address them during the QA session. Over to you, sir.
Thank you, Pooja. My great pleasure to invite all of you to this webinar. Senjas has been conducting such webinars on regular basis. Our intention is to ensure sharing of knowledge, technical dissemination of knowledge for the benefit of all the geotechnical engineering practitioners. So I welcome you all today to this presentation on forensic geotechnics. I'll be talking about the concepts and giving you also 3 case studies to explain how these concepts can be put into practice. Forensic geotechnics, the dictionary meaning of the word forensic is connected to scientific tests used by police to solve a crime. So obviously the word forensic has a legal connotation. And as a geotechnical engineer, you would be involved in trying to figure out the causes of a geotechnical failure and work out solutions. So this word forensic is of Latin origin, which means on or before the forum. Actually, a forum of noblemen used to be evaluating a criminal charge in the ancient times. And when you are present and argue the issue before the forum of noblemen or public individuals. So this is how the word forensic started to be used. So when we talk about forensic, it presupposes that a failure has occurred. It has resulted in some casualties, which may be loss of property, loss of human life, or injuries to people, inconvenience to the public. It may be breach of contract conditions. And finally, somebody has been blamed for it, and the matter has gone into court or arbitration to resolve this problem and to take to task the person who has been the cause of this failure. But one step before, if you can solve the problem before it gets out of hand, predict or not whether failure is likely to occur and take corrective action so that you can make sure that the problem is resolved. So that is what we are talking about here. That is the ideal role for the forensic geotechnical engineer. So the forensic geotechnical engineer should apply science and engineering within the rules and practice of the legal system. Effectively, you have to present the facts to resolve the conflicts. Now, there may be two ways in which you are involved in the project. Maybe as a policeman or a detective who is trying to figure out who is at fault. On the other hand, maybe you may be as a friend providing guidance for restoration of the foundation and resolve a problem and help avoid litigation and arbitration. So, if it can be done in that way, that would be the best. So, what does forensic geotechnical engineering involve? First, you identify the problem, investigate the causes, assess the risk. Then you review the structural details, the geotechnical data, predict the foundation analysis, perform a back analysis if you have the data to do it. Then identify the causes of failure or risk. Now, once you have identified the problem, you should be able to develop technically feasible solutions, uh, review the merits and demerits of each solution, select the final one, implement it, monitor it, and thus mitigate foundation distress. To resolve these kind of disputes, the forensic geotechnical engineer has a very important role. First, you collect data related to the failure, characterize the problem. It may be a failure or a potential failure which is identified that this thing is wrong and something can happen. So you characterize the problem, develop the failure hypothesis, and try to make a reasonable assessment of why the failure has occurred or is likely to occur. Then you do a back analysis and try to be realistic on this. If there are field observations are feasible, you do that, monitor the performance. Maybe a building is settling, so you can monitor whether the settlement continues or if it has been arrested. Then you do the quality control aspects so that you check whether there were any problems in the way the structure was constructed or anything else like that. Now, since data is never usually completely available, so you have to interpolate between limited data, make assumptions for analysis, and try to figure out what is the best solution. So here you have to rely on sound engineering judgment. So when you are developing your failure hypothesis and doing your back analysis, uh, let's try to make realistic assumptions and figure it out. I'd like to start by saying here that forensic geotechnical engineering is as much an art as it is a science. So, this is a borderline case here that it is not purely a science, and the ingenuity of the engineer is most important. So this is the flow chart of forensics. So once you identify a problem of an inadequate foundation or excessive settlement or possibility of failure or actual failure, first you review the structural details, the geotechnical data, perform the analysis, identify if it's a structural failure or a geotechnical failure. And if it's a geotechnical failure, predict the foundation behavior, what's happening. Then you work out the alternative foundation schemes, review the merits and demerits of each scheme, select the foundation scheme, implement it, monitor it, and hopefully the project will be back on track. Identifying the root cause of failure, that's important. And so the distress could be either due to the foundation, or it could be the structural problem. So if the problem is in the foundation, the geoprofessional uh, comes into action, and what he has to do is to act as a doctor with a healing touch and resolve the problem. So distress, as you know, could be man-made or natural. So we are talking of several possibilities, like ignorance of soil conditions. You didn't investigate the soil condition properly. Poor understanding of foundation behavior, wrong construction practices, misuse or damage of facilities, wrong estimation of loads, cover depth, or soil properties. uh, Additional load on the foundation was not taken care of, unusual site conditions not recognized, the problems. So you see here, my friend here is in quite a bit of distress, that a branch is just about ready to break, and he has to be saved. The forensic geotechnical engineer is in this kind of a scenario. uh, such poor quality construction or localized phenomena could lead to disaster or casualties. So, when we are talking about foundation distress, it could be a settlement failure, shear failure, or a serviceability failure. And in case of settlement failure, we are talking about total settlement or differential settlement, or even a lower factor of safety. In these kind of cases, the approach is the similar as the forensic, preferably without involving the court of law. If the matter has gone to the court, then it has to be resolved at the court level. But before you go to the court, if you can resolve it mutually, identify the problem, why the distress occurred, and come up with solutions which can be easily implemented, that would be the best. So you want to mitigate distress to ensure the desired factor of safety, to meet the serviceability criteria, to restrict further distress. That is, you want to make sure that there is no further settlement. Maybe you want to allow additional loads, vertical expansion. You are adding a couple of stories to the building, and of course to facilitate adjoining construction so that it does not cause any problems there. So mitigating distress, what you have to be doing first, you get the foundation details and the geology of the area, the soil data. Once you have these inputs, then you may want to do some investigation. So select the right kind of investigation to be done. Assess the reasons and nature of distress. Select your design profile, do appropriate analysis, and then work out the solution. So, when I'm talking about mitigating distress, I'm talking about steps which has to be taken before disaster strikes, or noticing the first signs of failure. So once I realize that there could be a problem, if we can solve it right there, that would be the best. So you want to do preventive action to avoid failure. So for this, what is important is that you have an experienced engineer. He can identify telltale signs of a potential failure and suggest and implement remedial measures. So when we are talking about foundation strengthening, there are various solutions. Stone columns, ground improvement. Maybe you want to do some retrofitting, install some micropiles, confine the foundations to restrict the settlement and to increase the shear resistance. You could be doing something to restrict the soil movement. This could be by grouting or contiguous piles, or other such solutions. Most important thing is to find out why distress occurred or is likely to occur. If there is an actual failure, you may be able to work out the soil parameters, do a back analysis, and then the design can be modified accordingly. Now, if there is a partial distress, a serviceability problem, you may not be able to do back analysis, but you have to be have enough ingenuity to identify the causes of what has triggered something which could be a big disaster, and solve the problem right before that happens. So potential failure is something, failure has not yet occurred, but it is likely to occur. The factor of safety is insufficient. There is an unreliable foundation. Building partly constructed already shows some excessive settlement. So to be able to construct it fully, then there would be a lot more settlement. So you have to take care of that. So you will have to rely on the available geotechnical data, boreholes, field tests, and lab tests, etc. Now, you need effective solutions that need to be implemented easily within a short time span with the help of locally available technologies that are cost effective. So the practicality of the solution which you are going to propose, that is very important. What went wrong, where, and why? These are the four W's of forensics. So, in forensics, we are talking about four W's: what went wrong, where, and why. So, in every case, you should evaluate this. This is the best way to identify the root cause. So the four W's are the key to understanding the problem and developing an appropriate solution. This can guide us towards the solution. Assess the likely foundation system that is required to ensure that the structure is safe. It is the investigative part of geotechnics, forensic geotechnics. So it involves a scientific approach. It requires understanding of the soil behavior, evaluate the structure response, and you have to do a soil structure interaction. Because understanding what triggered or caused failure, why failure occurred, can provide an insight to the type of restoration that will be required. Just give you an example of a few geotechnical failures which could be quite disastrous. So this is the Bhuj earthquake nearly 25 years back. It caused tremendous disaster in Bhuj, nearby places, even in Ahmedabad. This is a hill slope failure. You can see the slope failure here. This was a tunnel within a rock. So timely identification of this tunnel here in Delhi, it avoided a major disaster. Now let us take the case of the Leaning Tower of Pisa. This was a serviceability failure criteria. The Qutub Minar also experienced some tilting. Grouting of the soil and rock below the foundation was done to restrict further movement. This is the 1,000-pillar temple at Warangal. Some foundations of this famous temple of the Kakatiya dynasty had experienced distress. So stone columns were installed to strengthen the foundations and to provide confinement so as to restrict further movement. So now this temple is safe and working well. I now go on to present a few case studies just to demonstrate the use of forensic geotechniques to show how it can be used to identify and resolve geotechnical failures. So these are the three case studies which I'll be talking about. The first case study is of a failure of piles in a tire factory in Bahadurgarh, in Haryana. So this is where the project was in Haryana. It was a rubber tire manufacturing facility just north of Delhi. It is a steel pre-engineered building. Board piles of 600 diameter extending to 16-meter depth were installed. Each pile was designed for a vertical compression capacity of 50 tons. Two piles below each pile cap. During the erection of the steel structure of the pre-engineered building, settlement was observed in some of the pile caps. The measured settlements were more than 50 to 100 in places. Maximum settlement was obtained in this grid BB18 location, which I'll show you here. So this was the location where maximum distress was observed, and the next one, adjacent pile cap, also showed distress. So these were the piles which were involved in this. So a forensic study was taken to find out what the problem is. Prior to suggesting remedial action, the investigation was carried out in three phases. First was a detailed investigation to assess these strata there and figure out what happened. So boreholes and static cone penetration tests were performed. Then non-destructive tests were performed, low-strain pile integrity tests, and parallel seismic tests. These were done to assess the pile length. Then concrete coring was done through the piles to evaluate the continuity of the concrete and quality of the concrete for the clinching evidence of defects. So this was the scope of study here. In BB18, we did boreholes, static cone penetration test, pile integrity test, parallel seismic test, as well as coring of all the piles. In BB19, the distress was less. Pile coring was not done. Other tests were done. In the other groups, adjoining groups, we only did some boreholes and some cone penetration tests. Maximum investigation, as I told you, in BB18, because that is where the maximum distress was observed. So this is the boreholes in progress and the static cone penetration test being done there. Typical borehole data. What shocked us was that there was this zone here with very low SPT values. Below about 16, 17 meters, the N values were fine. But there were the zones where we got very low N values. So this was an issue of concern. The cone penetration test also showed a similar trend where we had low cone penetration tests till substantial depth, 11, 12 meter depth. Next was the assessment of the 4 Ws. So what went wrong? Why did the structure fail? So there were two theories which were put forward. First was that in situ conditions, there was natural variations. Maybe the initial investigation did not identify the problem. This was unlikely in this area. The other thing which could have happened was migration of fines caused by an improperly designed well point dewatering system. So the dwell point dewatering system was about 10-15 meters away, and that probably caused migration of fines. As a result, the soils moved away and the soil became weak. So it was clear that the pile settlement was triggered by these loose zones. The capacity has reduced because of this. You can see here that the groundwater is very shallow. It was probably a little bit higher during the construction period. Um, so the next step which we did was to check the structural integrity of the piles. So low strain pile integrity test was done. Excavation was done to expose the side of the pile. The low strain pile integrity test was done by impacting on the side. Later, the pile cap was dismantled and the test was repeated at the top. So this is what we got from the pile integrity test. We could see no toe response. Uh, so this was in BB18. Whether it was impacted from the top, from the side, or from the top, we were not able to get a proper identification of the pile toe, which means that the pile toe is probably not there. So we looked at mm, this pile 238. We hit the pile 6 times, but the data was very poor. Then, when we did the dismantling uh, mm, of the pile cap, you got some strong reflections at 3 to 4 meter depth, indicating a major defect. So also it indicated a weak toe reflection. The assessment was that around 3.5 meter or so, there could be some bulging, and then the toe was poor. So the PIT did not match the expected trends, suggesting possible defects. Uh, Both the piles indicated strong reflections at about 3 to 5 meter depth, which masked the data at deeper depth. So, major defect in could be necking or soil inclusions, and in pile 239 there could probably be some bulging. Pile length seemed to be okay, but we were not very sure of that. What was done to evaluate this further? Parallel seismic test was done. What is a parallel seismic test? You do a borehole adjacent to the pile cap. The depth of the borehole is a little deeper than the anticipated length of the pile. So we did 150 diameter holes to 30-meter depth, about 14 meters below the anticipated pile level, at a distance of 1 to 2 meter. Borehole was cased with a 3-inch PVC casing, and the annular space was grouted with a cement bentonite mix. The pile was impacted with a 5 kg handheld hammer, and two triaxial geophones were lowered into the hole at different depths. 1 meter interval, the readings were taken. So what you must do is you must look for changes in the wave arrival time. If the wave is traveling through concrete, obviously you will get almost the same wave velocity. And if the wave is traveling more through the soil, there will be a change in the wave velocity. So this is what was done here. The geophone being lowered into the mm, borehole for parallel seismic test. So we could see a clear break here, that below this level there was hardly any. This was soil here in these cases. In this, in 238, there was no clear change of slope. In 239, the The pile tip was around 13.5 to 14-meter depth, which suggests that the pile is short. The 236 in BB19 pile length is okay. Also in the other pile. But the key findings were that pile 238 in BB18 data quality is poor due to structural defects, and the other indicated it was shorter than what was anticipated. Next, we went to do some coring in the piles to confirm the PIT and parallel seismic findings. The objective was to confirm the pile structural quality and continuity. So, hydraulic rotary core drilling was done with a diamond bit. Double tube core barrel was used to minimize the fractures. Um, so this is what we got in pile 239. Below 12.5 meters, soil and weak concrete was encountered. So which means that there is a bad pile here below 12 meters. Now, when we did the coring, what was surprising is that in the top portion, the core recoveries and RQDs were good, but when I hit this weak zone here, my recovery and RQD reduced, which tells me that probably something has happened here. And this damage was at 5.67 meter depth, you can see here. What's happening? So nil recovery below 12.5 meter, that is a weak slush. So around 5 meters, there is a problem here. So when we did the pile 238, bent reinforcement pieces were found in the last core run at 5 meter depth. This pile may be bent or damaged at this level, so there is a discontinuity. So we got soil at that level. In the 239, we got it was breaking off at 12.5. The color of the return water was gray, indicating that still we are drilling through concrete, not soil, but probably weak slush. 14 to 15 meter, we got some reinforcement pieces. So all this indicated there is a problem here. So BB18, both the piles were found to be structurally damaged and had to be discarded. So additional piles were installed. So this is how the root cause of the failure was identified, and the remedial measures could be planned. The second case study is of an overhead tank on loose boulder fill in Gwalior, Madhya Pradesh. So this was a 18-meter high overhead tank close to an existing school. It was located in the congested area of Gwalior near the famous Gwalior Fort. So it was called the Killa Gate area. Here you got heterogeneous loose fill of stone and boulders, probably discarded during the construction of the fort, built in the 15th century by Man Singh Tomar. The fill is present to about 7 meter depth. The owner and the structural designer did not have any clarity on how to design the foundations of this overhead tank. Result was an unsafe and unreliable foundation design. So a routine geotechnical investigation had been done at that time. So the standard specification says you drill borehole to 15-meter depth or refusal, whichever is earlier. So refusal was met on the ground surface, so no data was collected. Because on the boulders, the refusal was met, and they did not go further. Then the structural designer suggested to do a plate load test. So they did a plate load test on a 30 by 30 centimeter size plate. The measured settlement was very small, so they thought that even a bearing pressure of 150 kilonewton per square meter is conservative. Now, the design was done for a 23-meter diameter RCC raft foundation at 2-meter depth. So excavation was done to 2-meter depth. On finding boulders, the excavation was carried out further to 4-meter depth. At 4-meter depth, further loose heterogeneous mix of stones and boulders in a sand matrix was met. It was at this stage that the contractor panicked. The owner was concerned that the strata may not be able to support the foundation. So the client then requested IIT Delhi and St. to evaluate the site conditions and suggest a solution. So I acknowledge here the contribution of IIT Delhi Professor Sahu and Dr. Professor Manna, who were part of this effort to solve this problem. So this is the condition which was seen there. So the loose heterogeneous non-uniform fill, you could see here, stone and gravels in a sand matrix. The stone may be part of the construction. Some of these were, well cut and prepared stones. So these have probably eroded with time, and loose pockets were observed in this fill. So several poorly constructed buildings in bad condition were present in the surrounding areas. Excavation has been carried out very close to these buildings. You can see here the foundation is exposed, and you can see this loose stone fill here. The excavation was very steep, nearly vertical. So these were all signals that there could be a disaster if you constructed the foundation at that level. So attempt was made to give lateral support to the building by stacking some material against the wall of the building. But you can see it is clearly inadequate. Doesn't work that way. So the main concern was the safety of a school building adjoining the excavation. At some places, they had tried to use cement mortar to stabilize the loose stones on the excavation wall, but evidently this is a poor effort. Such overhead tanks are usually designed on standard drawings, what is called as a conservative foundation design with limited assessment of soil conditions. It usually works because it is conservative. The structural engineer controls the design. The geotechnical engineer's input was limited or non-existent. As a result, very poor understanding of soil behavior, strata behavior, and lack of appreciation of the uncertainty in behavior of these loose heterogeneous boulder fill, and nobody knew what type of investigation should be adopted. Since the contract had been awarded, the approved budget cannot be exceeded. That was another issue. So what we found was that the fill extends to 7 to 8 meter depth. Being loose and heterogeneous, it is not a reliable foundation bearing material. So available geotechnical data is insufficient. No realistic borehole data. A result of 30 by 30 centimeter size plate load test cannot be extrapolated to design a 23 meter diameter raft. So no clear conclusions can be drawn, and evidently it is very clear that it is not feasible to support this raft on this boulder fill. So the action plan here, we perform a proper geotechnical investigation with four boreholes extending to at least 20-meter depth beyond the bottom of the fill. So perform SPT, undisturbed soil samples, and the complete range of lab testing, analyze data, and develop a. So you can see here the excavation which had been done. This was the condition. A working platform was you excavated to the bottom of the loose zone, and then a working platform was made, and the boreholes were drilled. Safety of this adjoining school building, particularly, was a matter of concern, but no failure had been reported. So, this is what the borehole data found, that below the loose fill of stones and boulders in the sand matrix, this extends to 6 to 7 meter depth. The natural soils consist of clay silt of medium plasticity, not expansive, it's alluvial in nature. So, to 23 meters, these boreholes had been done, and we found that the N values are increasing with depth, and groundwater was not met. So, in this fill, there is no you cannot rely on it, but below the fill, the strata is quite good. So, this is the natural soil properties below the fill. You can see here the shear strength is quite good. So the engineering solution was that the fill on the loose, heterogeneous, unreliable fill should not be done. It's not a suitable foundation bearing material. So foundations can of course bear on the natural soils below the fill. So restricting the total settlement to 50 mm, the raft can be designed for a net allowable bearing pressure of 225 kilonewton per meter square. Earlier they had designed it for 150. So raft diameter was reduced to 18.5 meter. Some saving in the cost, also reduced the excavation size, and also you won't get as close to the existing building as you thought it should. So a further excavation below the excavated level, another 3.5 meter was required, and the foundation construction may be taken up on the natural soils. What were the risks here? The excavation in the portion where it is close to the building needs proper monitoring. Some buildings are in bad shape, and some foundations are already exposed. So you need to be careful. So excavation is marginally safe. No failure has been reported. So here the lateral support system depends on how much risk the owner is prepared to take. We suggested that excavation may be done in localized stretches with temporary support to the excavation in small stretches. Somewhat risky but economical, so worth taking. Particularly if you can do the construction before monsoon, it will work. Another option was shotcreting the face of the excavation to stabilize. Of course, diaphragm wall is a very reliable system, but very high cost. Now I come to the last case study here for this presentation. I could go on and on with many more, but I will restrict to this one more case study here for a multi-story building, a deep excavation adjacent to a multi-story building in Gurgaon. So this project site, there was a 16-meter deep excavation for a new building adjacent to a six-storied existing building. The building outer line is about 6 meters away from the edge of the excavation. The basement of the existing building extends to about 5-meter depth below the ground level. The problem was that after heavy rains, part of the boundary wall of the building collapsed. And the boundary wall was at a distance of less than half a meter from the edge of the excavation. A soil wedge fell along with the boundary wall. So that's what happened here in this zone. The uh, boundary wall collapsed. It's very close to this existing building, which has a basement at 5 meter depth. And here, this excavation has been done to 16 meter depth. So that's what it looked like. This is the collapsed portion of the boundary wall. In the first panic situation, they removed the entire boundary wall so that there will be no further collapse of the boundary wall. So the first assessment which we did there was that nearly vertical cuts has been made, and even excavation to 16-meter depth looked to be stable. Erosion due to rainwater probably caused the instability. The boundary wall was too close to the edge of the excavation. So the exposed soils beneath the boundary wall got saturated during rains, developed a slip circle, which caused the failure. So the building owners, they feared that there could be some progressive collapse, and as a result, there will be their building, which has a basement at 5 meter depth, that could be affected. So they were ready to go to the court. So therefore, it was necessary to protect their building so that it remains safe, even if there is any further collapse. So the first step was the assessment of the geotechnical data. This showed that it is primarily sandy silt of low plasticity, and that is the reason why the vertical cuts remain stable. Cone penetration tests also showed that below 2 meter depth, the soil properties are good. And below 6 meter depth, it is really hard and compact. So, assessing of the 4Ws, the building appears to be safe in the present condition. But rains could trigger further failure. Progressive failure towards the building could expose the foundations constructed at 5 meter depth. To ensure safety of that building during the entire construction period, precautionary measures need to be taken. Possibility of further collapse of the soil needs to be arrested. So the solution that we proposed was that cement grouting of the soils adjacent to the existing buildings. This was selected as the time-saving and cost-effective solution. Grouting at the closely spaced points can effectively create a grout curtain. This can provide sufficient lateral support to the soils adjacent to the building foundation. So this is what was done. A borehole was made, 75 mm diameter. A concrete plug was placed up to the basement level, and using the grout pump, the cement slurry was pumped in. So 75 mm diameter holes to about 10-11 meter depth. We had 20 mm dia conduit pipe, and the hole was plugged at the basement level. So 2 rows of grout holes drilled adjacent to the basement line, close to the excavation. Along each row, the spacing was of the grout holes was about 1 meter, and these were staggered. So this is a mechanical grout pump which was used. The grout which was used was 1 bag of cement and 100 liters of water was pumped into the hole, initially under a pressure of 0.5 to 1 kg per centimeter square, gradually increased to 2 kg per centimeter square. The injection of the cement slurry was continued till further refusal to further grout intake uh, was met under a steady pressure of 2 kg per centimeter square. So the cement slurry was agitated continuously during the pumping process, uh, so that the cement does not set in the pump itself. So this is what the field results. You can see the two rows of grout holes, uh, mm, total of 84 points. The numbers you see here on these grout holes, these are the number of bags of cement which went inside. So we could do it quickly in less than 2 weeks. So substantial cost as well as time saving in compared to contiguous piles or sheet piles, etc. So this was successfully done, uh, and the construction was completed. So this is the completed retaining wall, and on top of this, a new boundary wall was constructed, and this boundary wall was supported on short piles, 300 diameter. Mm. So when we talk about geotechnical distress mitigation, one step before the court of law is involved, I'm talking about a fact-finding mission, not a fault-finding mission. So once you have the facts, you work out the solution and save the structure from major disaster or damage. So the forensic geotechnical engineer is a doctor with a healing touch. What he does is he evaluates the four W's, which is the key to the mitigating the foundation distress. So what you have to do is for the effective working of the four W's is a scientific approach with an open mind, evaluate the strata behavior, predict the behavior of this building, assess why failure occurred, work out the engineering solution, implement the foundation strengthening stream, monitor the effectiveness. So to be able to do this, you must do a detailed investigation of the causes and mode of failure, develop the engineering solution, uh, and solve this problem of failure or potential disaster. Most important thing here is sound engineering practice, because forensic geotechnical engineering, as I told you, is as much an art as it is a science. Thank you very much for your kind attention. I'll be happy to take questions.
Thank you so much, sir, for the insightful presentation. Now let's move on to the QA session. And I encourage everyone to keep posting your questions in the comment section and we'll address them one by one. So for today, our first question is from Ankit. And he's saying, how can forensic geotechniques be applied to aging infrastructure such as bridges and dams?
Thank you, Ankit. As far as aging infrastructure like bridges and dams is concerned, uh, forensics is very important and is being done uh, on a large scale. Particularly in Rajasthan, I know many of the old dams are being evaluated, and wherever problems are identified, solutions are proposed. The most important thing is to be able to identify what kind of problems could be there. Uh, Also, old bridges, wherever you find excessive cover or concrete may have lost its strength over time. Uh, if you can assess that, and the bearing capacities need to be reassessed. Earthquake stability is important. So, I mean, in fact, forensics is the right way to go for such aging infrastructure. Thank you.
Thank you, sir. Second question is from Karthikeyan. So, whether failure is documented in India?
It's a very interesting question. Most people try to, show the whatever successes are always documented, and people tend to show that I did this great thing, and but failure mm, in many instances are not documented. You try to hide it, and try don't let it be known, because there could be legal implications. That could be your reputation could be at risk. Mm, but I would encourage this, and let us document it and understand how failure occurred. And I always talk about fact finding, not fault finding. So, if you can ensure that the facts are put on the table, and mm, this is what happened, and this is the solution that was worked out, rather than trying to hide or even persecute the person who may be the reason why that failure occurred, the person or the company. Uh, uh, Very often, these things end up in court cases, and you want to, claim money from the other end to resolve the problem. So once that fear goes, I think people will come forward to document the failures. We have done it in many instances, mm, probably as a third party, when these case studies which I presented before you, and a few more, we have presented in various technical publications, in conferences and journals. Uh, you will find these papers, and I think they do a great service to the professional society, so that people will be aware that such a kind of a issue can occur, and take care. Otherwise, it remains undocumented, nobody knows, and everybody repeats the same kind of mistakes. Mm.
Yes, sir.
So
Thank you,
let's
sir.
try to avoid that.
Next question is from Hamir Hede. Sir, do we need to conduct 100% pile integrity test in structures supported by the pile foundation?
uh, Amir, very important that you conduct low strain pile integrity tests on most of the piles, as long as, if you are very confident that all the piles are okay, and whatever piles you tested you find they are good, maybe not necessary. But I would strongly recommend that you test 100% of the piles. And usually on a site you will find piles of different quality. So best to conduct low strain pile integrity test on all the piles, and because it's not a very expensive test. Secondly, after examining the results of the pile integrity test, you should identify the few piles which look to be the weakest. And if you can conduct your routine load tests on those piles, and if those piles pass, then you are confident that all the piles are safe, because the weakest pile is safe, so all the piles are safe. So that would be a quality assurance. uh, I agree with you that there is no mention on the in the IS code on the percentage of pile integrity test to be conducted. When we were, preparing this code on low strain pile integrity test, I happened to be part of the committee. We were debating about it, but the opinions that came from various experts was that mm, let us first get this as a part of the system and then talk about the percentage. So we did not want to insist on 100% or 20% or 50% or any percentage, but mm, it is important, and many companies like NTPC and others uh, nowadays demand 100%. The next version of the code will probably have a good percentage. There's also high strain pile integrity test which is being done. That also the percentage is not given in the codes, but we have to think about it. You have to be able to assure the client that the piles are safe. So that's what is. Thank you, Karthikeyan.
Next question is from Mohan Dagi. So, if there is a variation in the results from TIP and PIT, then which one is more reliable and why?
Uh, Mohan, I didn't get what is TIP. If you can just tell me what is the full form of TIP. PIT, I understand, pile integrity test. Uh,
Okay, so we will wait for his reply.
yeah.
Next question is from Mohammed Azhar. What was the most challenging geotechnical failure investigation you have worked on?
Oh, there have been many in my career. Mm, uh, Recently, we were, in fact, the investigation is still going on. There's a piling for a multi-storied building. It was a 26-story. It's a 26-story building. When they did all the piles without doing any initial load test, and at the end they did a few routine load tests just to reconfirm that they are okay, and they found that the pile is not carrying even 50% of the design load. The safe capacity of the pile was less than 50% of the design load. So right now we are about 150 piles have already been installed, and now the project is at a standstill. We are trying to work out the solution so that this 26-story building can be constructed without any risk of failure. Right now, this is the challenge which I'm working on. Uh, Hopefully, we'll have a solution soon. Thank you, Azhar.
There is a reply from Mohan Dangi. TIP is for thermal integrity test.
Oh, yes. Thermal test is apparently very good. Uh, I have seen the results of one or two tests, but only thing is that thermal integrity test, the equipment is not so much easily available in the country, although some companies are having it. Uh, uh, as far as which one is better is tough to answer. If either of them show a defective pile, it needs to be investigated properly. In fact, the equipment manufacturers of TIP, they claim that TIP is more reliable. Uh, but ultimately, the proof is in the actual pile, checking out the pile. If you find a defect, you need to investigate it. Same way, you see, if like in the case study I showed the results of the PIT, we didn't find a proper toe response. Um, you just can't sit on that. You'll have to figure out why is the toe response bad. Maybe you want to do a high strain pile integrity test. Maybe you want to do pile coring. You have to, maybe you want to even do a static load test. Uh, and figure out if that pile can still be used. You see, there may be some defects in the pile, but that doesn't mean that you have to reject the pile. If the pile is still able to carry the load, it's fine with minor defects.
There's another question from Amir again. Sir, if a particular pile low tests pass but failed an integrity test.
I will go for the load test because load test is a proof of what actually load the pile can take. As I was just saying, that could be as far as integrity test is concerned, there is nothing like pass or fail. All it will tell you is that there is probably some necking or bulging at some depths. It may tell you that the toe response is weak, and why the toe response is weak could be because of various reasons. Mostly, it is due to a weak toe, which means that slush at the bottom. Uh, but as long as the pile passes in the load test, that's the final proof that the pile is okay.
Uh, Next question is from Upasna. Sir, can you suggest some remedies for seepage induced failure in earthen dam slope?
Upasana, there are various solutions which has been implemented on various project sites, right from grouting to you know treatment at the toe to ensure that you can guide the seepage in the particular way. Even closely spaced piles. There are several solutions. Each case study will have to case will have to be evaluated individually, and then you have to take a call.
Um, Thank you, sir, for answering the questions. Next question is from Arjun. Have you encountered cases where multiple geotechnical factors contributed to failure? How did you isolate the root cause?
Becomes more challenging. Very often there are multiple factors, and one factor triggers the other. Um, Many may be independently. Uh, mm, so you have to be aware that there could be once there are multiple causes, then one type of failure may one cause may in fact mask the other. Something is more dominating, that is what will be uh, actual result in the failure. So as I said, geotechnical, forensic geotechnics is an art. So you have to use the science of geotechnics to very carefully sift through the evidence that you have got and then come to a solution.
Our next question is from Ahmed. Are there industry guidelines or best practices engineers should follow for failure investigation?
That's a tough one. Uh, in fact, I'm not aware of industry guidelines, but there are various experts who have talked about this. There are books by international experts on forensic geotechnics. Uh, you can probably find them online or in Amazon. There are various books available, but these are only IRC has given some guideline. But you see, the problem is that the cause of failure could be many, and you cannot document every possible situation. So the only guideline is that follow your gut, try to identify the root cause of failure, and the four W's are what you should be looking for. And once you have that, you should be able to work out your solution.
Next question is from
Thank you,
Gurmeet.
Amar. Yeah.
What lessons have been learned from forensic studies that have influenced national or international geotechnical designs and standards? Design standards.
Well, it is for us to learn from the failures, and most of the codes are written with the intention that the structures should not fail. Uh, and but what direct influence they have had on the uh, practices, I am not aware.
Uh, Today's last question we're taking from Anita. How does forensic investigation help in designing more resilient infrastructure?
Anita, if you are designing a new structure, forensic does not come in. Only the standard engineering practices come in. Forensics come in when there is either a failure or a risk of failure. So once you identify that there could be a failure, or if there is actual failure, doing the right kind of remedial measures obviously ensures that your infrastructure is resilient.
Oh, thank you, sir. There's one more question from Vijay Kanagi. And he's saying if the initial load test results are higher than calculated capacity by 50%, then can we increase the pile capacity? If yes, how much?
That's a very interesting question. I keep getting this question. Uh, the If your calculated capacity is much higher, it probably means that the initial investigation was little conservatively estimated, or but to make sure that you can increase the pile capacity, what requires to be done is that you need to test more. If uh, one initial test is done on the entire project, then maybe very difficult. If you are going to have multiple initial load tests on the project, that is also not financially viable. So you have to be able to take the right kind of a decision. You can increase the pile capacity, even anything between 20 and 50%, but then you should go beyond the IS code and test more than that 2% of the piles which the code gives. Let's test all the do a low strain integrity on all the piles. Make sure that you have good capacity, good condition on all the piles, and very often the initial load tests give you very good results because the supervision in the initial load test is very good, and once the routine load test comes, the supervision may be uh, important. Yes, Mr. Gupta had suggested some documents which may be used. Um, I would add to that. And then, on the basis of the load settlement behavior, you can take a call on whether the piles can be increased or not. There is no direct rule on how much you can increase the capacities.
Thank you, sir, for addressing these questions with such clarity. And a big thank you to all our attendees for our active participation and engaging questions. Before we wrap up, mark your calendars for our next webinar on mitigation foundation distress, scheduled for 17th May. Stay tuned for more details and feel free to connect with us on social media or email for any further queries. Once again, thank you, sir, and thank you everyone for joining us today. We look forward to seeing you at our future events. Thank you, sir.
Thank you very much.